Good afternoon, everyone. My name is Swarnim Shirke. I'm a PhD student at IISc, Pune. I thank the SOC for giving me the opportunity to present my work at the 42nd ASI meet, and I'll be presenting a recent work of mine, which was published in JCAP. Here is the QR code of the paper if you want to go there. This was carried out along with other co-authors, Suprabhu and Debarati Chatterjee from IISc and Laura Sabunski and Yogen Dilip from Goethe University, Frankfurt. It was carried out under the Elements collaboration, and I've also recently joined LSC collaboration. So I'll be talking about, this is the title, ARMOR is a new probe of dark matter in neutron stars. So the first thing I would like to mention is the neutron decay anomaly. So we know neutron is not the lightest baryon we have, so it decays to proton plus electron and antineutrino. So to measure the time scale of this decay, there are two methods. One is bottle and trap method, which are denoted by this red and green, this black error bars, where you count the number of neutrons that have decayed, and the other method is beam method, where you measure the number of electrons that have been created electrons. So when you do this, you find that there is a discrepancy in the two time scales. So you have more number of neutrons decaying, but you don't get as many number of protons. So in 2018, so Bartosz Forman and Benjamin Grinstein, popular paper, introduced the idea of this dark decay channel to explain the dark matter. So they had certain constraints, and to also explain this anomaly. So to explain this anomaly, the requirement was that the branching ratio of this neutron decaying into the dark sector, the branching ratio is around 1%. So 1 in 100 goes into the dark sector. So if we carry this forward to neutron stars, I won't give an introduction because everyone is here is familiar, but here is a schematic of the interior. And we know at the interior we have neutron-rich matter. And if we have such a channel where neutrons can decay into the dark sector, we also speculate whether there is dark matter inside these neutron stars. Also, just like heliocosmology, there are different oscillation modes for neutron stars, FP, depending on the restoring force that we have, and one particular mode called as R modes, oscillations. These are toroidal fluid oscillations in rotating stars, and the Coriolis force plays the role of the restoring force. And it was shown in a mechanism called the Chandrasekhar-Friedman-Schulze mechanism, that if the neutron star is rotating above critical frequency, then these oscillation modes become unstable, and their amplitude keeps on growing, and this gives this leads to copious emission of gravitational waves apart from other sources. So unstable R modes is also a source of gravitational wave with a higher breaking index. And this is a purely relativistic effect, and affects transport properties of neutron matter, such as shear viscosity and bulk viscosity of the matter are responsible for damping these unstable modes so that they don't go out of control. So it is usually shown in this curve. If you look at the black curve, this is omega versus t. So above this black curve, the frequency is higher, we get unstable R modes, and neutron stars, these modes become unstable, and the neutron star starts spinning down, giving out these gravitational waves, and comes down. And once it comes into the stable region, again the spin down stops, and we get like just pure cooling. So this curve is defined by this balance of time scale at which the gravitational waves are like making the modes unstable, and the damping from the shear time scale of shear viscosity and bulk viscosity. And one thing to note is that low temperatures the shear viscosity is more efficient, and at high temperature we get bulk viscosity. So when we come to dark matter, we don't need an introduction. So I would just like to point out that recently people have been studying the effects of dark matter accumulation at neutron stars, because given their high density, and mainly they consider the mechanism for this as the accretion. The dark matter particles are accreted, but we don't get high dark matter fraction in such a case. Here in this model, since we have neutrons decaying into dark matter, so we are generating dark matter particles within the bulk itself, and we can get high dark matter fractions as well. So, and people also, so we have such a scenario where we have neutron stars and also now dark matter within it. There are different models for dark matter which people study. The main question that we ask is, what is the effect of this on R modes? And no one has studied this before. There were 2 papers who calculated like shear viscosity, but that's it. Using this model, we go ahead and calculate the shear viscosity, bulk viscosity, and calculate these effects and actually see if we get any effect on our modes. So to model, I will quickly tell. So this is for hadronic matter, we use the relativistic mean field model where we have nucleons, protons, and neutrons interacting via different mesons, and there are different couplings for this interaction, which are set by certain observations that are done in the lab itself. So these are the parameters which dictate these couplings, and we use 2 such parameters for some specific reason. And for the dark matter, we have this neutron going into dark sector chi plus phi. So chi is a fermion, so we have a Dirac scalar and this phi meson. Plus we add a vector repulsion between these dark matter particles, so they're self-interacting, and so we get a energy density for dark matter, which is the free part, plus a number density square type interaction. So we fix the mass to 938 MeV, and this G is a free parameter that we have, and we have this over the lifetime of neutron star. We establish this chemical equilibrium because this time scales of this decay are much smaller than the time scale of neutron star life. So from this condition, we can calculate the properties of bulk matter. So on the left, I'm showing in equilibrium when we have all these conditions set in with different density at x-axis. For zero interaction, what is the amount of dark matter we get in a bulk matter? So this is shown by the purple curve. So for zero interaction, we have this high fraction of dark matter, and others are other nuclear species like neutron, proton, and electron. As we increase the interaction, the amount of dark matter goes down. As energetically it becomes more difficult to form these particles. And same effect is observed on the equation of state. So for zero interaction, we have a new degree of freedom, so the equation of state becomes really soft. We don't get as much pressure. But as we increase the interaction state, it goes stiffer, and this black curve is the one, or this last one, where we have no dark matter. So usual nuclear equation of state that are considered to model neutron stars. When we solve the TOV, the Tolman-Oppenheimer work of equations, from the equation of state, we get a mass radius curve. So with this dark matter effect, we see that we need a certain amount of interaction between these dark matter particles to have a mass radius curve that exceeds the 2 solar mass case. So it is a well-known observation. So any equation of state should generate a neutron star which forms at least this one observation, which has been observed around 2 solar mass. And from this, we find that this interaction parameter G has to be greater than this 5.6 Fermi square in the units that we consider. And from interaction, we also can get constraints on this dark matter fraction. As we increase G, we see the dark matter fraction, which is the amount of dark matter we have quantified by mass to the total mass of the neutron star, that goes down. And if we use this constraint, we see that in such a scenario, the maximum fraction of dark matter we can have is 38%, which is already a lot. But we have further constraints. Like if we take this limit on G, we can actually calculate the cross section, so self interaction cross section between dark matter particles, and we get this sigma by n value somewhere around greater than 10 raised to minus 3. Plus, we also have some already from astrophysical observations, we have certain constraints on sigma by n. It is usually 0.1 centimeter square per gram to around 10. So we just consider a more lenient limit, 100 here. So we get this limit on G as well. This constraint was also put forth by one of the previous studies, but they had considered one particular model, and we make a generalized comment here, and it's a more general constraint that can be applied. Also, using this cross section, we estimate the shear viscosity in kinetic theory, and we find it to be low compared to the shear viscosity from other sources like the neutron scattering, electron scattering, which is there in neutron stars. Also, for bulk viscosity, this is the expression, and it depends on the tau. So we need some process which goes back and forth when we have density oscillations. So due to this phase lag between this equilibrium, time required for this equilibrium to establish, you get bulk viscosity. So we need to consider this time scale at which these processes occur. And we also have a part on this P, which depends on equation of state, so which further depends on this parameter G. But we found that the results don't change if we vary G, we don't have much effect. So the main parameter is tau. So we need to know what is the time scale at which these processes are happening. So if you are changing the density at what time scale are these neutrons going into this dark sector and back. And these are the standard direct Urka and modified Urka process, which is there for normal nuclear matter as well. So just forget the due to paucity of time, just forget the plot on the left. So on the right, so here we need to know the time scale for this process. We consider 3 different scenarios. One, because the microscopic matrix element for this decay channel is the model. There are multiple models. There is no constraint on it, so we cannot have any particular model that can derive the temperature dependence. So we borrow it from the modified Urka process, the temperature dependence of the time scale. So in first case, we take it 100 times. So one constraint we have that this time scale should be 100 times that of the normal neutron to proton decay that comes from the neutron decay anomaly itself. So in the first case, we do it 100 times the time scale for the modified Urka. The second scenario, we keep the time scale fixed, so it's not dependent on temperature at all. You get to see the general variation for any particular temperature dependence. And in third case, we do it 100 times the direct Urka time scale, because given the number of particles, the temperature dependence, given the phase space considerations, would be closer to that of the direct Urka. And here, this result, so this blue dots is the instability window that we get without any dark matter. So in scenario 1, which is represented by this orange line, it lies exactly on the blue curve. So we don't get any modification in this particular scenario. In scenario 2, where we fix the time scale constant, now it's independent of temperature, we see that we get a flat curve where this is where the dark matter by viscosity dominates. And for different time scales, we see for lower time scales it gets modified very significantly. And in scenario 3, so we see that we get this brown curve. So this bulk viscosity, which is the high temperature part, is where the dark matter plays a role. So we do get a modification in this case. So these are the 3. This is the main result. There are more results, but this is the main thing that I'm showing. So to summarize, so yeah, we just investigated the R modes, effect of dark matter on R modes. And we have considered certain models. We take constraints on G as well as dark matter fraction. We find the shear viscosity to be negligible, as well as the effect of this interaction parameter G to be negligible on the instability window. We find a significant variation in the instability window for 2 of the scenarios, and we see that the data that I had plotted on this previous curve can be explained in the constant time scale scenario if the time scale is pretty low. So that is there. In future, we can see other models and also go for more microscopic realistic calculation of shear viscosity. So, thank you.